for example, let's start the debugging time. So we've looked at the interrupts, we've introduced the interrupts, we've introduced the priorities of the interrupts, and then we looked at the VOS exit ISR and what does it do. So let's have a look at a bug, and then let's debug this and look for the problem. During this debugging, we will find that there is some optimizations of the compiler. So essentially, whenever you're working with compilers and debuggers and linkers and that stuff, you have to know your tools. So I'm going to show you how we are debugging this piece of code. So this is the code. Let me connect the board and burn the code, and I'm going to show you the bug and how we could resolve this. Okay, so let's upload the code. Now it is erasing. Okay, so as we can see, when we load the new VM, the LED blinks and then stops blinking. So this is a interrupt example. So if we open, for example, Zerynth examples, if we open this, and search for interrupts. So interrupts is here. So this is the example of interrupts. Basically, it attaches an interrupt on the button pin, which is in this example, it's button 0. So I am attaching an interrupt on this button. Whenever I press it, interrupt will be triggered. So is it triggered on the rising edge or the falling edge or both? This is defined here. So on pin fall, the interrupt will be triggered on the fall edge. On pin rise, it will be triggered on the rising edge. So when it goes from 0 to 1, this is the rising edge. When it goes from 1 to 0, this is the falling edge. So this is the example. Let's compile and uplink the code through Zerynth Studio. Okay, so let's open the serial console. So this is the serial console. Supposedly, there is an interrupt attached on the button. So whenever the button is pressed, this function should be executed, which should print something and then blink the LED. But if we try it right now, nothing would happen. So the interrupts are not working. So, and this is the bug that we want to, essentially, we want to look at and what happens, essentially. We want to look at this problem. So typically when we tend to face something like this, we will look at the head of the problem, essentially, and then we're going to dig deep and then eliminate the options. So we are calling onPinRise, and what does onPinRise call? onPinRise essentially calls this function, which is onPinRise or fall. So onPinRise or fall eventually calls this, which is valPin attach interrupt. So essentially, valPin attach interrupt attaches an interrupt on this pin, which is the first argument, to that function. So the first thing that comes to my mind when I'm debugging something like this is I should test valPin attach interrupt alone. I should put it aside and test it in a separate testing case. I've done that, and pin attach interrupt works fine. So this is not a problem. So what is the problem? Either the pin is not attached correctly, the mode, or the function, or something else. So let's have a look at the function that the interrupt is being attached to, which is val vm add irq slot isr. So this function, which is defined in here, essentially it looks, this function essentially what it does is that when the interrupt is triggered, it looks which interrupt is triggered and on which edge. So if the button 0 is triggered, that's okay. If this is the rising edge and I have configured the full edge, don't do anything. If this is the rising edge and I have configured the rising edge, then please execute the code. So the function, what it does is that it executes this specific code related to this specific interrupt. What is interesting is that it takes slot and direction. So it takes a slot, which is the number of the interrupt, and the direction which is either a 1 or 0. So we don't know what the source of the bug is. So we should look at how this function behaves on other boards, and then we're going to look at how does this function behave on our board, and then see what the difference is. So let's run the debugger and then see the behavior of the code. So this is the OpenOCD, which is the interface for the debugger, and this is the ARM GDB debugger. Let's connect target remote localhost. Okay, now we are connected to the board. So let's have a breakpoint at this function, which is vm add IRQ. Okay, so right now we have a breakpoint at this function. Let's press continue. So if we press this function, you would find that this function is called. So as I said, this function is called whenever an interrupt is triggered. And if we press continue, it would continue. But press again, the function will be called. As I said, press continue, you would find that the function typically is called twice, because this function should be called on the rising edge from the change of fall to rise and from the change of rise to fall. So this function should be called twice, essentially. If I press the button correctly, it should be called twice. So press continue and press the button. We're going to find that this is the first time that the function is called, and the second time the function is called. Do it again. First time function is called, second time function is called. What is interesting, you would see that every time the slot is number 15. So 15 is the interrupt slot for the button, which is correct. But the direction is 0. So this is wrong. This shouldn't be 0. This should be 0 and then 1. Because as I said, interrupt is triggered from rising edge to falling edge, and then it is triggered again from falling edge to rising edge. So this should be 0 and this should be 1. This should be 0 and this should be 1. So right now there is something wrong with the direction. So let's have a look at the direction and see what's happening essentially. So the direction is an argument. So who calls this function? This function is being called here. This is the HAL layer of the Atmel software framework of Microchip. So this function, this is exactly when I call the callback of this argument, I'm calling the function that we are referring to. So we are sending 15. I've hard coded it to be 15 for this example. So we are sending the slot, but we are sending the direction. So the direction should be either 1 or 0. Fair enough. But the direction is always 0. So there is something wrong happens here. So there is something wrong that happens essentially on the direction. So the direction is the output of GPIO get pin level. So we have gone from there is a error in the interrupts to there is an error in this line. So we have pinpointed the error exactly. So right now we know that there is an error in this line because direction is always 0 and it should be 0 and 1, 0 and 1. So why does this function return always 0 or always return 0? So the first thing that comes to my mind is to take this function and test it outside this code. When you do that, the function works with no problems. So there is a problem with using this function in this code. I'm going to show you the code and then we're going to see what the problem is. DIR, which is the direction, is an 8-bit character. So this is a variable that has a size of 8-bit, 1 byte. So supposedly I'm going to call this function, execute it, which gets the level of the pin, of the pin that is triggered, the button. and then the return function is the level of the pin, and then the return function should be sent back to the direction. So where is this function GPIO get pin level? This is in the HPL layer of the Atmel standard software framework. This is the implementation. So let's have a look at this function if it works correctly. So let's have a look at the compiler. So supposedly this function is being called whenever there is an interrupt, because this function calls that function. So let's cut all of this call series and just go to this function directly. So let's go put a breakpoint on this function. Stop, put a breakpoint on this function, and then press continue. So let's trigger an interrupt. Right now we have triggered an interrupt at GPIO get level, because as we have discussed, this is the function that is executed before the BM add IRQ slot. So as you can see, this function is executed. Let's press next, temp, let's press next, temp, and we are executing in here. But if I press another next, it will exit the function. This is very interesting because I'm not returning any value. So this function, which is the GPIO get pin level, essentially does not return a value. It is executed, but it doesn't return anything. So this is very strange. So why doesn't it return anything, although it is executed? On deeper look, or a more concentrated look, this is an optimization from the compiler and the debugger, because GPIO get pin level, if you look for the declaration of this function, you would find that this is a static inline, as we've discussed before, unsigned 32-bit. But we are using an 8-bit variable. So we are using essentially an 8-bit variable. So the question is, does it make a difference? So what we want to have is, we want to have a 1 or a 0. So does it make a difference to have an 8-bit variable hold the value, or hold the return value of a 32-bit value return function? Let's have a look at what the debugger tells us. Like, let's press continue and then trigger the interrupt again. So right now we are continuing the code. Let's trigger the interrupt, and we are at the same function. Press next, press next. Let's print the value of TMP, and supposedly, so TMP is the return value, because we are calculating TMP, which is the temporary variable, and then we are returning it. So in normal sense, this should be returned. But if I printed TMP, you would find that this is a very large number. If I print the hex of TMP, you would find that it is hex 83 and a bunch of zeros. So what happens here? What happens is that this is the return value of a 32-bit integer. But you're trying to put it on an 8-bit in an 8-bit placeholder, on an 8-bit character. So the microcontroller or the compiler basically look at this, and it looks at the first 4 bytes, and it says that the first 4 bytes are zeros, then the value should always be 0, and that's it. So essentially what the compiler has done is, the compiler has optimized our code and ruined our code in the same way. So the compiler has optimized our code because this function returns a 32-bit value, and you want to put it in an 8-bit variable. So what happens is that it looks at this variable in this line, it finds that the first 4 bytes are zeros, then the result is going to be always 0, and then it's not going to return anything. And this is an optimization thing. So essentially the compiler said, I will execute the function because you told me to execute the function, but I will not return any value because it's always going to be 0. So what is the solution for this? The solution is to just return a 32-bit value, and that's it. So let's compile and uplink. These kind of errors are related to how the compiler is written and how is the compiler developed. So these kind of optimizations, although they might slip during development, but these are very important because they are trivial. Essentially, if I want to show someone what's happening, this function is a 32-bit and its value should be put in an 8-bit, but the compiler basically decided that it's not going to return anything. So it's going to execute the function, but it's not going to return a value. So let's compile the code and then uplink and then upload the code and then look at what happens if we put a 32-bit value instead of an 8-bit value. Okay, it takes a long time because we have configured the compiler with the with the compilation options of code size, essentially because it's, as I said, it's important. So the compilation time is not really the best. Okay, so let us stop the OpenOCD. Let us quit the debugger, uplink the code, erasing, programming. Okay, so let us upload the same example. And then open the serial terminal. Okay, now if we, this is the same example and the same code, if we press the button, you would find on the serial terminal that it printed touched, which is the ISR, so it is triggered exactly or as it should, and the LED is blinking. So we fixed the bug essentially. And the best part is looking at the debugger after we fixed the bug. So let's open OpenOCD again and let's look at the GDB debugger and look at what happened essentially. Localhost. Okay, so let's look at the function which is vmirq slot. As you can see, when we are when we had the bug, essentially every time, as I said, it's called 2 times every interrupt trigger, but it was called with a direction of 0 every time. So let's have a breakpoint on this function and then press continue. Let's trigger the interrupt. You would find that it is triggered on direction 0, which is okay. But if you press continue, you would find that it's triggered on direction 1, which is what we have set. So we have successfully fixed the bug, essentially. So just to sum up, what was happening is that we were trying to cast a 32-bit variable or a 32-bit return value into an 8-bit. So the compiler basically optimized this into looking at the variable in the middle and then saying, okay, I'm going to execute the function, but I'm not going to return any value. So this was a very interesting bug. Let's have a look at another bug. Essentially, let me ask you a question. What is better, to use Boolean like Boolean X, so it should hold 2 values, 0 or 1, true or false, and then execute a function and then cast this value to a Boolean, or X and then execute this function and then use the item this operator, which basically checks if it's a 1, then put a 1, if it is 0, put a 0. So what's the difference between these essentially? The question is, what's the difference between using bool and using this operator? The difference is that in the compilation time, the difference Boolean is developed somewhere and is written somewhere in the compiler according to the documentation of the compiler. So Boolean, in many compilers, Boolean are declared as any value other than 0 is a 1. It doesn't have to be 1. And that's the problem with Boolean, because Boolean doesn't have to be 1. So if the value of Boolean is 10, then it's for Boolean it works with no errors. But for your function, you might be expecting a 1 from it. So the second implementation, which basically checks if it is anything, so put a 1 instead of it, is better, because you're not relying on the Boolean implementation. You are 100% sure that the result of this optimization is a 1 instead of a 0. Okay, so we have a question on the chat. If you have questions, feel free to add them on the chat. Would it be possible to be notified of this problem during compilation time? It will be possible if the interrupt driver is written in a way to assert, basically to check if, like as we've seen in the GDB debugger, basically this function gets called with the rising edge and with the falling edge. So if the driver is designed in a way to assert, to check for these values, it should be notified during compilation time, essentially.